works, the way this litter manipulation works is you can take a litter of animals. Usually a litter of rats is around 8 to 10 animals. You can actually put 2 litters with one mother so that you have 18 to 20 animals per one mother. That's litter expansion. So those animals, if they have 18 to 20 baby animals, those animals do not get fed very well because there's just so many of them. Okay? So this is what Dr. McCants did. He took normal litters, and then he had another litter that was expanded, and then from day 0 to day 21, while they were nursing, he had the normal litter over here, and you can see that by day 21 there's actually a big difference in terms of weight gain. Okay, these are the litter expanded animals down here. These are the normal. But if you look at the rest of their lives, when they get to be considerably older, what happens? The litter expanded group remains low in their weight. Now, what happens if you restrict food later on? This is weeks now, and they restricted food for 3 weeks in some animals that were already young adults. What happened to these young adults? They bounced right back when they got back to a normal diet. So what this tells us is that during the first 3 weeks of life, this is a critical window during which undernutrition can actually lead to lifelong consequences. Okay? And they call this programming. Now, one of the problems with this technique is that if you want to feed the mother a certain diet or do a litter expansion, one of the problems is that you really don't know how much the baby is actually eating or what the composition of the diet is that the baby is actually eating. So one alternative is what is called the pup in the cup model. This is something that we use in our own laboratory at the University of Florida. There's a few places in the world that are using this model. And what this entails is you anesthetize the baby rats, and then you place a gastrostomy tube into their stomach, and you place the pups, one animal, into a little styrofoam cup in a water bath at around 39 to 40 degrees centigrade. And each one of those animals is being fed through a tube in the stomach with these syringes, automatic syringes. And so what we can do is manipulate the diet of these animals. You can give them high carbohydrate. You can give them high protein. You can really do pretty much what you want in terms of feeding these animals for a short period of time. Now, what I want to do is go through some studies. These are some studies that have been published by Dr. Srinivasan Patel, and they use this pup in the cup technique to look at long-term outcome, short-term and long-term outcome of these animals that were fed different quantities of carbohydrate and lipid. What they did was they placed a gastrostomy tube at 6 days of age, and then when they were around, right around the time of weaning, when these animals go to a regular diet, they took out the gastrostomy tube and then followed these animals over time. The diets are seen here. Carbohydrate diet. 56% of the diet was carbohydrate, 8% control. And they made this isocaloric by increasing the fat in one group and decreasing the fat in the other group. Now, the rationale behind this is that a lot of babies get fed high carbohydrate foods. For example, one of the things that a lot of babies get is juices and supplementary types of carbohydrates. Not so much in the neonatal intensive care unit, but when they get a little bit older, we give them high quantities of juices and certain carbohydrates. And so Srinivasan Patel wanted to look at the effects of these higher quantities of carbohydrates in this animal model. So what did they find? During the gastrostomy feeding period, up until day 24, there was no difference in growth. They were all getting pretty much the same calories. There was similar growth until day 55, despite similar diets. But then from day 55, the high carbohydrate fed rats grew more quickly than the control rats. And after 100 days, they had full-blown obesity, 557 grams versus 710 grams in the control versus the high carbohydrate males. This was only seen in the males. The difference in obesity was only seen in the males and not in the females. Then they looked at biochemical adaptations. Remember, we were talking about early adaptations during fetal life. Well, here they're starting to see adaptations with postnatal feeding. Here are some of the examples of the adaptations that they saw. This is postnatal age, and this is the period of time that these animals were on the experimental diet. Okay, here's plasma insulin, high carbohydrate. Plasma insulin higher in the high carbohydrate group. Okay, and then they looked at PDX1, and this is a pancreatic duodenal homeobox gene. This is a gene that is involved in the production of new islet cells. Okay, and so the gene that is involved in the production of new islet cells was very high in the high carbohydrate fed group. They took out the pancreas of these animals. This was around day 14. They took out the pancreas, separated out the cells, put them into culture, and treated them with glucose. And here you can see in the group that had the high carbohydrate, they had the greatest insulin secretion. Now, that was at the time that they were getting these experimental diets. What about later on when they had been off of the experimental diets for about 80 days, at 100 days of age? Okay, for about 80 days, these animals were eating just normal, their regular diets. Okay, remember this is what we saw at 12. This is 100 days. Plasma insulin concentration remains high in those that were getting the high carbohydrate fed diet. And that's with blood glucose. That's the same in both groups. So these animals were programmed with that early high carbohydrate diet to have a higher insulin level when they got to be 100 days of age. And that also fit with the obesity that was seen in these animals. And the same thing held true if you look at if you take out the pancreatic islet cells, treat them with glucose at 100 days, again, you had higher insulin secretion from the pancreatic islets. Okay, so that's these animals when they got to be adults. What happens when you take the mothers or the female animals who were fed the high carbohydrate diet, let them grow to adulthood, mate them with normal males, and then you look at their babies. Remember I said before that this programming may involve more than one generation? Well, here we see in the animals, and again, this is only in the males. When they get to be 20, 30 days, here's when they're all having normal diets fed from their mothers. They are no longer in the pup and the cup model. Then at around 40 days here, you start to see a divergence where the insulin concentrations are much higher in the progeny, the second generation animals of those whose mothers were fed the high carbohydrate diet. So this is telling us that mothers who are fed a high carbohydrate diet in their infancy, during infancy, may actually put their babies at a risk for type 2 diabetes when those babies get to be older. So this is just a summary. First generation, here's the prenatal period, here's the suckling period where they get put in the different formula. You start seeing an increase in weight gain at 55, abnormal glucose tolerance test at 75, obesity at 100. Second generation, increase in weight gain starting at similar times over here in obesity, and increased insulin secretion during this period of time also. Now, what are the mechanisms for this? We really don't have a good understanding of mechanisms, and several hypotheses have been raised. And one of the hypotheses is the epigenetic hypothesis. Okay? Now, remember, genetics involves 4 base pairs of DNA: adenine, thymine, guanine, and cytosine. Okay, and how that you have mutations in DNA that can cause genetic problems. Epigenetics does not involve mutations in adenine, guanine, cytosine, etc. Okay, but what it does involve is access of transcription factors to the DNA molecule. Okay, now the way this works is in each one of our cells we have a nucleus that contains DNA. And if you spread out that DNA from one nucleus, it's very long. It's about 1 meter long. Very thin molecule, but it's very long. That molecule is wrapped around protein molecules called histones. Those protein molecules can change their configuration. And if you have acetylation of the histone, ubiquitination of the histone, or if certain molecules attach to the histone, that histone can actually unravel and allow more DNA to be open for transcription factors to cause transcription to occur. Okay? So acetylation or modification of histone is one way that epigenetics can occur. Another way is you can have methylation of cytosine and guanine residues on DNA, and that will then shut off the transcription. Okay? And we are just in the early phases of learning how this relates to nutrition. There are several studies that have been done with this, and I don't have the time to get into that, but certainly epigenetics is something that we are very interested in terms of early nutrition and some of these findings that Srinivasan and Patel have been seeing. In our own laboratory, we've started to study protein effects in the neonatal diet. We're looking at this early protein hypothesis, seeing if large quantities of protein, very similar to the Srinivasan and Patel studies, actually might have some effect. Our very preliminary studies, we have not yet published this, but the preliminary studies suggest that higher intakes of protein early on, you can see some early metabolic effects, but we do not see adult obesity, and we do not see adult type 2 diabetes or hypertension. But those studies are still very preliminary. We're working on that yet. Let me just go here. So let's talk about what we can do practically for these babies now. Now, early undernutrition, as I mentioned before, can lead to a thrifty phenotype. And if you give normal age-appropriate nutrition to these babies, you'll most likely have a healthy adult. They may not be completely grown to the same degree if they are given totally just normal for appropriate nutrition, but in general they should be healthy. However, early undernutrition, and you get this thrifty phenotype, and you have overnutrition, in other words, this red line here, where you push the babies really hard, then you might have some metabolic problems in the adult. And again, as I mentioned before, this remains very hypothetical. We don't have very strong evidence for this yet, but there is fairly strong evidence that if you do not have catch-up growth, that those babies will be neurodevelopmentally delayed. So, recommendations. Remember that early nutritional perturbations may alter subsequent health status as an adult, and that these effects may be passed on through generations. Recognition of these risks should be accompanied by a nutritional lifestyle that may need adjustment based on these risks. And research needs to be aimed at determining mechanisms of these early adaptations that result in later disease.